Hello everybody and welcome. Today we are going to discuss the solution to the problem array nesting. It's a medium problem and we're going to discuss a very intuitive solution and an approach to how to actually think about things. But first, let's talk about the problem itself so we are on the same page. You're given an integer array nums of length n. Now this nums has a special property saying that all of its numbers are in the range 0 to n minus 1. Basically, it's a permutation of numbers in the range 0 to n minus 1. The goal of this problem is to return the longest length of a set sk. So you have to find the longest of these sets. Now, how do you define a set s of k? First, you'll select the index k. Let's say we select the index k. Now, we're going to take the nums of k and add it to the set. Now we have nums of k in hand, which now is going to act as another index. This nums of k acting as an index now points to nums of k, which we are also going to add in the set. So on and so forth, we can go to nums of k and so on and so forth. We stop adding right before a duplicate element occurs. Basically, as soon as you find a duplicate, end this right here. Okay, so maybe once we find this k, we can do this sort of logic, which can take maybe order of n time. But to find k, maybe also taking order of n, right? Actually, let's formalize this and we'll look at the brute force solution first. So we'll iterate over I in range of n, basically 0 to n minus 1 both inclusive. And for each of these indices, we'll maintain a set. This is the s of k. In this case, I've called it s of I. While there are no duplicates in this loop, go ahead and add the nums of I. And I now becomes the nums of I itself. This is maybe a tricky line for a beginner, but it makes a lot of sense. Okay, once you build this set, you find a duplicate, you'll break out of this loop and you'll check if length of s is greater than the answer. Maybe it's a previously stored answer, you'll check it against. And if you found a longer set than the answer, then go ahead and save that as the answer. In this case, what is the time complexity? We are iterating over each and every single element, so order of n here. And inside of this, we have a while loop, which may also be order of n, worst possible case. So it's the time complexity of order of n squared. At the same time, the space complexity is order of n because in each iteration at every single point of time, we're going to have to maintain this s set, which can be order of n. There can be n elements in the set or n by 2 or whatever in the order of n. And so we'll have to keep that in mind. But this is just the brute force solution and maybe we can build something from it. It always helps to think about a couple of examples, a couple of simple examples that can help you build maybe an intuition about how to go about things. Let's take the case of 0. This 0 element is at the index 0. So index 0 points to element 0. We'll put that in the set. This is element 0 now points back to itself. And so we'll end it and this break this loop right here and the set is 0. This looping around may be important, so we'll keep that in mind. What about 0, 1? In this case, we have the index 0, which points to 0, which again points to index 0. So it's a loop again. Similarly for 1, so there are two loops actually running simultaneously. Again, the answer remains length of this set or this set, which is just 1. What about 1, 0? 1, 0 is where things can get a bit interesting because now at the index 0, we'll look at the element 1, add it to the set. So we'll add it right here. Now this element 1 is now going to act like an index. So it's going to be pointing at 0 here, which now we're also going to insert into this set. And now this 0 goes back to 1 here and we'll end it because we've found like a complete cycle. Cycle is the keyword here because it looks like these loops and cycles are what we actually want to look at instead of these sets. Actually, let's remove the notion of sets and just look at cycles. And we'll come to a bigger test case soon. But first, 2, 1, 0. Index 0 points to 2. Fine. 2 points to 0. So It's like a loop again. In this case, the answer is 2 because the length of the cycle is 2. Okay, let's take things to the next level and look at a bigger test case. This is the one given in the question. Okay, we'll start off with the index 0, 5. 5 goes to index 5, which is 6. Goes to index 6, which is 2. Goes to index 2, which is 0. And 0 points back to this. The length of the cycle is 4. In fact, this is the answer to the solution. Feel free to enumerate other cycles in this, but 4 is the longest possible one of them. It also looks like we can simplify this problem a lot. Instead of keeping these sets as the primary focus, we observe something. The answer for index 0 is the same as the answer for index 2 or 5 or 6. All of them belong to the same cycle, so all of them will have the same answer. Even if you start at the index 6, you will end up in the cycle of 4 at the index 6 again. And that's the beauty. You can just maintain this visited sort of list. And if you already have an answer for this, if you already have an answer for 0, you'll have an answer for 2, 5, and 6. And so you'll just need to check once in the visited list whether a particular index has been accessed or not. By the way, very sneaky thing, but since you are maintaining this visited list, you can sort of store it in order of n space, but at the same time, you're only going to visit every element once. So the time complexity is also now going to be order of n. Amazing, right? And this points to the no need of maintaining a set. We can just have this visited array and that will take care of itself. Let's actually code this up and we'll understand this better. So what's the first thing we want to do? Let's extract out the very basics. Nums will also have this answer. What is the smallest possible answer, by the way? We saw those self loops which meant length of the set to be 1. So answer will keep that in mind. What else do we need? We need a visited list. So we'll have 0 n times. Now we're going to go over each of the elements, just like we saw in the trivial in the brute force solution. And for each of them, now I want to check how good of this index is. So let's maintain a temp, which is going to count the number of sort of edges in that cycle. Okay, now we say while not visited I, while this particular element has not been visited, go ahead and do some computations. See, if it has been visited, we have already sort of considered it previously, so we don't need to look at it again. And once we find this temp, we can just write answer equals to the maximum of answer and temp, at the end returning answer. Okay, what is the computation here? If you haven't visited that particular index, first go ahead and visit that. Now, at the same time, if you have visited a new index, you want to increase the temp by 1, right? The length of the cycle is increased by 1 now. And each of this time, I is going to get to the nums of I. This is the same logic as we saw in the brute force one, I equals to nums of I. And this wraps up our solution. I'm going to submit this once more and accept it. This again runs in the space-time complexities of what? Order of n each. The order of n in space is going to be this visited array. And this visited array forces all of these nodes to be accessed only once. Forces all of these nodes to be visited only once. And so the time complexity is order of n again. And that is it for the solution of array nesting. Thanks a lot for watching.